So now let's try some examples. So if I look at example number 1, this is a limit as x approaches 0. So the first thing I'm going to do is just try to plug a 0 in. Now if you're plugging a 0 in, that means I can drop the limit notation because I'm evaluating the limit. So this is going to give me, and again I'm going to use arrows instead of equals, 3 times 0 minus 2 e to the 0 over secant of 0 minus 0 squared. Well, 3 times 0 on top is 0. E to the 0, anything to the 0 power is 1. So that's going to be 0 minus 2. Secant of 0 is the same thing as 1 over cosine of 0. And cosine of 0 is 1. And 1 over 1 is 1. So this is 1 minus 0 squared, which is 1, which gives me a value of negative 2. So I use the equals in between here because these statements are actually equals. I'm going to use the arrow here because I'm plugging in and showing that I'm evaluating. I don't think they would get super picky about using an equals in this spot. But if you're ever not sure, use the arrows. All right, example number 2. Again, the first thing I'm going to try is plugging in a 0. So if I plug in a 0 to the first part, that's going to give me 7 squared, which is 49. And let's see, that's going to give me minus 35, minus 14, which gives me 0. And then plug a 0 to the bottom, that's going to give me a 0, which is indeterminate form. So I am indeterminate form. Now, I'm going to go back and look at my options here. I'm going to use the definition of a derivative. The reason I know to look for that is because this is the limit as h approaches 0, and there is an h on the bottom. If you go back up here and look at our definition of a limit, those are 2 key features. I also see that I have f of x plus h minus f of x. So now I need to go see if I can figure out what my function is and what I'm evaluating it at. So if I look at this, this looks like they have plugged in, it looks like they plugged in a 7. So this is going to be my f of x plus h. And then this is going to be my f of x. So it looks like my function is x squared minus 5x. So I need to find the derivative of that. So 2x minus 5. And then it looks like they're wanting me to plug in a 7. So f prime of 7 would be 14 minus 5, which is none. So there's my limit. Just a hint as to where that 14 came from. The 14 is if they had taken f of x. So if I think my value is a 7, if I plug a 7 into my f of x, just to double check that, I should get a 14. And that would be 49 minus 35, which is 14. So that just confirms that that is just plain old f of x. Example number 3. Again, I'm going to start by just plugging in my negative 1 and evaluating my limit. And that's going to give me 1 plus 3 minus 4, which is 0. And the bottom is going to give me 1 minus 7 plus 6, which is also 0. So again, this is indeterminate form. I'm going to try, this looks very cute and quadratic and probably factorable, so the first thing I'm going to do is try to factor it, which is one of my options that I have under indeterminate form. So if I factor this, and that cancels, And when that cancels, I know that that was the problem area, because when I plug a -1, that's the part that would have produced that indeterminate form. So now I can just plug in my -1. Okay, now make sure you understand here, and we're going to add this to our exam tip. In this step right here, I still have my limit notation because I have not evaluated the limit. I have not taken the limit of anything. Now I'm getting ready to plug in my -1. So now I can drop the limit notation and just do -1 minus 4 and -1 plus 6, which gives me -5/5, which is a -1. So I drop the limit notation there because I'm evaluating my limit. So on my AP exam tip number 3, I'm going to say drop limit notation only after evaluate. So I wanted to do one more example. So I've added this example 4, and I think you're fine just to watch it. If you want to try to squeeze it somewhere in on your paper, that's fine. But I just wanted to do one because this one, if you plug in a 2, you're going to get 0/0, which is indeterminate form. But this one, you can factor, but it's been a while since we factored 4 terms, and that's going to pop up enough to where you need to make sure you know how to factor 4 terms. So I'm going to leave my limit notation because I'm not taking the limit of anything. And to factor 4 terms, you group the first, it's called grouping. You group the first 2 and you group the second 2. So for the first group, I'm going to take out a 3x, and that's going to leave me with x minus 4. You always bring down that middle sign, so it's going to force you to take out a negative, and then I can take out a 4. Now remember, you're not just taking out a 4, you're taking out a -4, and that leaves me with x, oh, I'm sorry, I missed a square right there. That's going to leave me with x squared minus 4, and that's over x to the 4th minus 16, which can factor with squares to x squared plus 4, x squared minus 4. And then with the grouping on top, I see that these 2 are the same. So again, I'm keeping my limit notation because I have not pulled the trigger on a limit yet. I'm going to pull the x squared minus 4 out. It's going to leave me with 3x minus 4. And then I have the x squared plus 4, x squared minus 4 on the bottom. And those are going to cancel. So now I can do the limit as x approaches 2 of 3x minus 4 over x squared plus 4. And I can plug in a 2. So it'd be 6, that'd be a 2 on the top, and an 8 on the bottom, which reduces to a 1/4. Now notice I dropped the limit notation there because I evaluated my limit. You could also do this problem with LHOP. If it's an FRQ, remember you have to be super careful with that notation, which again we will go over in detail later, but this is just another method you can use if it's an FRQ and you don't want to go into LHOP. I just want to make sure that you're comfortable with factoring 4 terms. Okay, so now let's talk about continuity. A function f of x is continuous at x equals a if, and this is a very formal definition that is most likely going to pop up on an FRQ. So the first part is that the limit, as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. Just means they have to be headed in the same direction. But you know that just because the limit from the left and the limit from the right exist doesn't mean that the function exists at that value. Remember, the limit is just where is it headed. So then you have to come in and say, all right, then also the limit as x approaches a, which means from the left and the right has already agreed that they're headed to the same place, of f of x must equal f of a, f of that value. That means that once you're headed there, there is actually a dot there. There's a hole there. So if we look at types of distance discontinuities, this is when these two parts of the continuity definition are violated. So there are three types of discontinuities. First we have removable. So removable just means that you have a graph that has a hole in it. And we'll call this hole, we'll say his x value is b. So you can see with your eyeballs that we are not continuous. Analytical, a hole is going to happen when you have, and this is at x equals b, so when you have like x minus b over an x minus b times an x minus a. And you can see that these two factors would cancel. And you remember that when two things cancel like that, that produces a hole. So the way that you're going to say this is you're going to say the limit as x approaches b of f of x does not equal f of b. So this violates the second part of our definition, this guy right here. So for the second type of discontinuity, it's called a jump discontinuity. What it's going to look like on the graph is you've got a function and then it jumps. I have to have an open circle on one end and a closed circle on the other where they would have connected, because otherwise it wouldn't pass the vertical line test. So this would be a piecewise function. So we would have f of x equal to some sort of function where for x is, and if we say this happens at b, for x less than b, and then another type of function for x greater than or equal to b. And they don't match up. So this violates the first part of our definition of derivative. So we would say the limit as x approaches b from the left of f of x does not equal the limit as x approaches b from the right of f of x. And you really have to really flex when you do an FRQ and really show this beautiful notation showing that you know the definition of a limit. For the third type of discontinuity, this is infinite discontinuity. So this is going to happen at an asymptote, and we'll call this b. So you've got a graph that does that and that. So analytically, what that's going to look like is it's not going to be like your whole, your removable discontinuity where your factors cancel. This you're going to have like x minus a over x minus a, x minus b. So I can see that this would be removable, but at b, I have a vertical asymptote. So I'm going to say that the limit as x approaches b of f of x does not exist. And my reasoning is because f of x tends towards infinity. So now let's look at some practice. Okay, so let's look at example number 1. It says, is g continuous at x equals 2 and justify? This is a piecewise function. Now the word justify, I'm going to put that down here under your exam tip. Justify uses a definition or a theorem. It means you need to have a because in your answer. So is g continuous? That's a yes or a no question, but the justify is usually where most of the points lie. So if this is a piecewise function, the first thing I need to do is test the first part of my continuity, because that's what I'm testing. So I'm going to test my limit from the left and my limit from the right, and I'm going to really work on my notation. So I have the limit as x approaches 2, because that's where the break is, of g of x, but I need to test it from the, let's see, this one would be from the left, and then I also need to do the limit as x approaches 2 from the right of g of x. Okay, well the one from the left would be the limit as x approaches 2 from the left of sine of negative pi over x. And to evaluate a limit, the first thing I'm going to try is just plugging in my value. So sine of negative pi over 2. Notice I dropped my limit notation because I'm evaluating it at a specific value. And negative pi over 2 is at 0, negative 1. So that value is a negative 1. And now for my second limit, I'm coming in to the right, so I'm going to use this function down here because those are for all the values greater than 2. So I'm continuing with my limit notation because I have not plugged in a value yet. And now I'm going to plug in a 2. So that's going to give me 4 minus 12 plus 7. 4 minus 12 is negative 8, and negative 8 plus 7 is a negative 1. So I have proven the first part of my continuity, but the next thing is, so I know that from both sides we are headed towards a negative 1, but now I just need to make sure that g of 2 gives me a negative 1. Well, to evaluate g of 2, I'm going to go into the top function because that has the equal to underneath it. So I'm going to do sine of negative pi over 2, and that's going to give me the negative 1. So I'm going to say yes because the limit as x approaches 2 from the left of f of x equals the limit as x approaches 2 from the right of f of x, which equals f of 2, which all equals a negative 1. So this is sort of a one-stop shop for both sides. I'm saying that from the right and from the left it exists, therefore the limit exists, and that this also equals the function at that value. Therefore, this function is continuous. So this is my justification. Okay, example 2 says the graph of f of x is shown above. Which of the following statements is false? It's a very easy word to overlook. So 3 of these should be true statements, and we're looking for the one that's false. So the first one says the limit as x approaches 3 from the right and the left are equal. So here is 3, and as we approach 3 from the right and from the left, they are headed to the same place. So that is a true statement. B says the limit as x approaches 6 equals f of 6. And yes, as it approaches the right and the left, that's the same place, which is also where it is filled in. So this is also a true statement. C says the limit as x approaches 5 is a negative 2. And I can already tell that's false because as I approach 5 from the right and 5 from the left, those are two very different places. So that is a false statement. So I think it's C, but let's check D just to make sure. This heads to negative 1 from the right and negative 1 from the left and to negative 1 from the right, and it's saying that they're not true. And that is a true statement. Those limits are not equal. So this statement is true. So I'm going with C, but watch out for words like. Okay, and then I've just added another example. We'll call this example number 3, and I think you're fine just to watch. So I've got a piecewise function here. It's got some a's built in. It says for what value of a makes the limit as x approaches 3 of f of x exist. Well, you know, for it to exist, that this side has to equal this side at 3. So we're going to take that concept and just write it in terms of math. So 3ax squared minus 2ax must equal 5ax minus 4x at x equals 3. Well, if x equals 3, I'm going to plug a 3 in and just solve for a. So if I plug in 3 in there, that's a 9, so that'd be 27a minus 6a equals 15a minus 12. And 27a minus 6a is 21a. Subtract the 15, so 6a equals negative 12. So a equals negative 2. It didn't ask me to justify anything. It just said for what value of a. So I found it. So 1.3 talks about end behavior. And end behavior is what happens to the graph as it heads to infinity or to negative infinity. So we're going to talk about horizontal asymptotes, but we're going to talk about them in terms of limits. So anytime you refer to a horizontal asymptote on the AP exam or in calculus, you always want to back that up with a limit. So this would be the limit as x heads to infinity of f of x, or the limit as x heads to negative infinity of f of x. Now, for rational functions, you know this from your work from pre-calculus. If the degree of the numerator is larger than the degree of the denominator, in other words, if the top degree is bigger, that there is no horizontal asymptote. If the degree of the numerator is smaller than the degree of the denominator, or the bottom is bigger, then you know the horizontal asymptote is y equals 0. And if the degrees are the same, you know that the horizontal asymptote is going to be y equals a over b, where a is the leading coefficient of the top and b is the leading coefficient of the bottom. Now that's if it's a rational function. If it's not a rational function, then you need to think about how things are growing. If I ask you for the limit as x approaches infinity of x to the fourth, well, you know that function looks like this. And so as x heads to infinity, you can tell that there are no horizontal asymptotes, that this function is headed to infinity. It is not bounded. If we talk about log functions and exponential functions, you need to remember what log functions look like and what exponential functions look like. And the fact that exponential functions grow extremely fast and log functions are not bounded, they grow, they just grow very slowly. So let's look at our examples. So to look at the first one, the first thing I have to notice is that I'm headed to infinity. So I know that I'm thinking about end behavior. This is not a polynomial over polynomial, this is a rational function over polynomial. So I'm really just interested in the highest powered terms. So square root of 16x to the fourth is going to be 4x squared, and the bottom is a 3x squared. So if I evaluate the limit as x heads to infinity, I know that the power, the degrees of the top and the degree of the bottom is the same. So I know that this limit as x approaches infinity of this function, I'm just going to call it f of x, is headed to 4 over 3. And that's just using my asymptote rules. Example number 2 says which of the following functions has y equals 0 as a horizontal asymptote. So if I'm a polynomial function, I know that I want the degree of the numerator to be smaller than the degree of the denominator, or I want the denominator to be bigger. And if I look at A is tempting me to think that way because they have the leading coefficient as a 5, but they have put this out of order. You have to look at the highest powers leading coefficient. So these two degrees are the same, so his limit as x heads to infinity of f of x is going to be 8 over 3. No, 8 over 11, sorry. Because the degree is 3 on the top and the bottom. So not headed to y equals 0. If I look at B, B's top function is a degree 4. The bottom function is a natural log. So I know that this is going to grow very fast because it's a degree 4. It's that W. So as it heads to infinity, it's headed north. It's headed to infinity. And this is going to grow very slowly. So if I have the top getting much bigger than the bottom at a faster rate, I know that it's headed to infinity, so not headed to y equals 0. So I know both A and B are out. For C, this is a degree 5, again, growing very quickly, just like the top of B. So this guy's growing very, very fast and headed to infinity. The bottom is e to the x. E to the x grows faster than a polynomial function. So I know that this is growing fast, but e to the x is growing faster. So when the bottom's getting bigger, quicker, then that fraction is headed to 0. So I'm thinking it's C. If I look at D, if I'm plugging in infinity into the bottom of this one, I know that this fraction is headed to 0. However, this is 3 minus 0, which would be 3. So the answer has to be C. And your exam tip for this is always demonstrate calculus methods when justifying results. So you've dealt with asymptotes, horizontal asymptotes all your life, not all your life, all your mathematical last couple of years, and so just don't rely on that. Make sure that you're tying it into calculus. So when you're talking about a horizontal asymptote, always make sure that you're writing it as a limit as x heads to either infinity or negative infinity. Okay, last video for day 1. So this is the intermediate value theorem, or the IVT. This is a very important theorem. Odds are it's going to be used on the AP exam, and they are very particular about what they want to see and how they want to see it. So let's talk about when you're going to use it. And these are the conditions. The only thing that has to be okay to use the IVT is f of x has to be continuous. On the closed interval a to b. So f of x has to be continuous on a to b. What? All right, so this is your conclusion. Then f of x attains or hits every y value between, now it's not between a and b. A and b are x values, so it's between f of a and f of b. And the example I used when I taught this was, if you are 1 foot high when you are, I don't know, 6 months old, and you are 6 foot tall when you are 20 years old, is there an age in between 1 year and 20 years where you are 4 foot tall? And the answer is yes, because height is a continuous function. So at some point between 1 year and 20 years, you had to hit every height between 1 foot and 6 foot. So the y is the when will we use it? We will use it when they tell us to prove that a given, and that's important, function attains a particular value. Prove that you were 5 feet tall at some point. Okay, and then the how. Since f of x is continuous on a to b, and f of a equals some value, and f of b equals some other value, then you're going to say that the IVT guarantees that, and you're going to state your conclusion, which we're going to practice. So before we jump into this example, let's do a couple exam tips. So the first exam tip is when you use the IVT, check conditions and relate the theorem to the problem. And then write conclusion. The second exam tip is that you must state explicitly how you know the given function is continuous in order to use the IVT. So how do you know continuous? So sometimes it'll just straight up tell you that it's continuous, but sometimes it's going to say, hey, the function is differentiable, and then you need to state, because I know that f of x is differentiable, therefore it is continuous. So just put your Captain Obvious hats on and state. They just want to see you acknowledge that you know that it has to be continuous, the function has to be continuous, and then how do you know that? The other thing is that's super good for an exam tip is to incorporate the question stem into your answer. So use question stem. If you're not sure how to word your answer, just go restate the question in a statement. Okay, so let's go knock out this example. It says the rate at which a shop sells candy bars in bars per hour is given by the differentiable function. Okay, now don't just gloss over that. That's super important. Differentiable function C of t, where t is measured in hours after the store opens at 9 a.m. So t equals 0 is 9 a.m., so this would be 10 a.m., 11, 12, 1, and this would be 2, 4, and there's 5 o'clock. Selected values of C of t are given in the table below. Okay, now selected values means selected values, and you don't know what happens in between these times. It says, is there a time C for where C is in between 1 and 7, so in between 10 o'clock and 5 o'clock, where the rate at which the candy bars are sold is exactly 50 bars per hour? Justify your answer. Okay, so I can tell that this is asking for for me to find a particular value and to justify that that particular value exists. So that's how I can tell that this is the IVT. So the first thing I'm going to do is I'm going to state my conditions. So I have to be continuous. So I'm going to say since C of t is differentiable, then C of t is continuous. So now, and again, I'm looking back at my notes where it says how. It says since f of x is continuous. Okay, so I've got that part. And then it says f of a equals some value and f of b equals some value. So I'm talking about in between 1 and 7. So I should say continuous for the closed interval 1 to 7. So now I need to find f of 1 and f of 7. So I'm going to say since f of 1 equals 52 bars and f of 7 is 25 bars, the IVT, and this is really important to call it by name, the IVT guarantees, nope, I spelled that wrong. Let's try that again. There we go. guarantees that there is a time in 1 to 7 when the rate that candy bars are sold is exactly 50 candy bars. Now, I'm missing one piece. The IVT says that I have to be continuous, so I have that part. Since f of 1 is 52 and f of 7 is 25, I know that I can be 50 candy bars because 50 is between the 25 and the 52. I have to say that. So because 25 is less than 50, nope, is less than 52. So I have to show that 50 falls in between those two y values. So since c of t is differentiable, then we are continuous on the closed interval. F of 1 equals 52, f of 7 equals 25, so the IVT guarantees that there is a time in 1 to 7 when the rate that candy bars are sold is exactly 50 candy bars because 50 is in between 25 and 52.